All right, so now we move on to Unit 2, which is Exponents for our final exam review. And Exponents was a pretty tricky unit, but I'm hoping that this review kind of jogs your memory a little bit and that you're able to break it down into these rules that will help you organize the way you solve for these solutions. Okay, so if we look at exponents where we have an exponent of 0 or 1, well, those have a specific evaluation. We're going to actually see that here. Well, anything to the power of 0 is automatically going to be 1. Now, we need to be careful because if negatives are introduced here, that's going to impact what our solution is. But overall, whenever we have something raised to a power of 0, we know it's going to become 1. So let's consider the first example here. 5 to the 0. Automatically, this is going to be equal to 1. Well, below it, right below, we have 5 to the 0, which is 1. But the negative is not included with that exponent. The exponent does not affect the negative. So you're going to write negative, and then 5 to the 0 is 1. Negative 5 to the 0, when it's in brackets like that, that means the negative is included. So negative 5 to the 0, both the negative and the 5 get the 0, so we know that this is just simply 1. And then if we go to the example right next to it on the right, we have a negative 5 to the 0. Well, the negative 5 and the 0 that are included within the brackets, these are all going to become 1. But then we have that negative floating on the outside here. So this is going to be negative 1. And then finally, 5 to the 0. Well, 5 to the 0 is going to become 1. But then we have that negative floating on the outside that is not connected directly to that exponent. So we know this is going to be equal to negative 1. Now, let's look at things that have an exponent of 1. Anything raised to a power of 1 just becomes itself. So 17 to the power of 1, that's simply just 17. Negative 17 to the 1, well, that negative is floating out front. The exponent isn't connected. So we put the negative again, but 17 to the 1 is 17. Now, negative 17 to the 1, this is an odd exponent. 1, 3, 5, 7, all the odd numbers. When we raise a negative to an odd exponent, it's always going to stay negative. So this is going to be equal to negative 17. So if you have an odd exponent, it's going to be negative. If it's an even exponent, that negative will become a positive. And we'll see that maybe in some of the later examples here. All right, product rule. This introduces one of our first rules besides 0 and 1 as our exponents. Product rule refers to when you multiply things with a common base, what happens to their exponent. So in this first one here, well, b squared times b4, that means our common base is going to be b. And then we add the exponents. 2 plus 4 is equal to 6. So I'll expand it on the first one just so we can see it. This is b to the 6. Negative 3 to the 4 times negative 3 to the 5. Negative 3 is our common base. And then we have 4 plus 5. 4 plus 5 is equal to 9. Now, what we could do is we could expand this out to get an actual specific number. We would realize that the exponent here, just like previously discussed, is an odd exponent. And an odd exponent that applies to a negative, this number would end up being negative, and then we could expand 3 to the 9. But for this example, I'm just going to leave it with that common base. We have a base of 2 to the 2x times a base of 2 to the 4x. Well, our common base is equal to 2, and we add those exponents, 2x plus 4x. 2x plus 4x, this is going to be equal to 2 to the 6x. All right, 3 a4b5 or a4b1 times 5ab negative 2. Okay, what we're going to do is we're going to first multiply the numbers out, because if we have coefficients that are just simply integer numbers or some form of fraction, let's just multiply them. 3 times 5 is equal to 15. a4 times a1. If it's not written, there is a 1 here. So that means we go 4 plus 1 is a to the 5. Okay, now we have b. There's no exponent there, so we're going to write in a 1. b1 times b to the negative 2. That's like saying b1 minus 2. 1 minus 2 is going to give me b to the negative 1. And here's where the problems in exponents really wanted you to be thinking ahead for final solutions, is you have to put everything in terms of a positive exponent. So our final answer is therefore 15a5 divided by b1. anything that's a negative exponent, whether it's in the numerator or denominator, is going to flip to the opposite location. So if it's in the numerator and it's negative, it goes to the denominator. If it's in the denominator and it's negative, it goes to the numerator, which we will see tons of examples of, but we want to make sure all exponents are positive. Okay, quotient rule. So opposite of the product rule where we add our exponents, in quotient rule, we subtract our exponents. So b12 minus b, or b12 divided by b5, well, b12 minus 5, or b12 minus 5 is equal to b to the 7th power. Okay, we go down to the example right below, x to the 6 divided by x to the 2. We could rewrite this as x to the 6 over x to the 2 because it means the same thing. Division is division, so you could either write it vertically or horizontally. And this is going to be equal to x6 minus the 2 from the denominator, which is x to the 4th power. Now, a way to confirm that we got this right, which you can even do with the product rule, is to say, well, more importantly with the quotient rule, where were the b's greater, in the numerator or the denominator? Clearly, they're the greater in the numerator here, so we should get an answer where b is in the numerator. Similarly, is x to the 6 greater or is x to the 2 greater? We know 6 is greater than 2, thus the answer should have a solution where it is in the numerator as the positive. All right, let's go over to our example here. 4 over 3 to the 6 divided by 4 over 3 to the 2. What we can do here is say, hey, we know that it's just going to be the fraction, and more specifically, because they share the same base of 4 over 3, where the base is represented by 4 over 3, what we can do is say it is equal to 4 over 3, 6 minus 2. And then if we simplify this 4 over 3, 6 minus 2 is to the power of 4. So if we really wanted to, we could write brackets here too, just to make sure that that is applied to both. Now, we could expand this just like we did in the previous problem, and we would know that 4 over 3 to the power of 4 is also equal to 4 to the power of 4 over 3 to the power of 4. And we're going to come to that when we deal with power rule, but for now, we want to just say that quotient rule is when we subtract the exponents with a common base. Okay, now we go over to our next example here. We have x, y, and z, 3 variables, x, y, z. We're going to start with our x's. x7 divided by x2, that is x7 minus 2. We then go to our y's, which is y. y3 over y1, because remember, when it's not written, you could put a 1 there. y3 over y1 is like saying 3 minus 1. And then finally, we have z4 over z4, which is 4 minus 4. So now let's simplify this. It's x to the power of 5, y to the power of 2, and then z to the power of 0. Now we should remember from the first page, anything raised to the power of 0 simply just becomes 1. Now, do we need to multiply whatever we have by 1? Not really, because we know that that would just give us the same thing. So what we could do here is just simplify it as, yeah, this goes to 1, but anything times 1 just gives us the same thing that we had there. Okay, and then our last example on this page here, we have 3 over 2, m-1 over m-3, n-4 over n-positive 3. Well, right away I'm thinking, okay, 3 over 2 isn't going to reduce anymore, so I can keep the 3 over 2 as is, because that won't reduce anymore. 3 over 2, they're both prime numbers, they're already fully reduced. What I could do now is flip all the negative exponents from the numerator to denominator or the denominator to the numerator based on where they are. So what I'm going to do is I'm going to flip m3 to the numerator, because I took the denominator that was negative and then brought it to the numerator and made it positive. I'm going to do the same thing with m to the -1. I'm going to bring it down to the denominator and make it positive, because we know as soon as it flips, it can become positive. I'm going to do that same thing with n to the -4. I'm going to bring it down and multiply it here. N to the -4 came to the denominator and joined the n to the 3. Okay, this is equal to 3 over 2. m3 over m1 is like saying m3 minus 1, that's m squared in the numerator. And then we have product rule in the denominator here. Two things with a common base, different exponents, we're going to add those together to make n to the 7th power. And there's our final answer. Now, here's a really easy way to confirm that you did the right thing in regards to getting your solution and that your m and your n are in the right place. When you look at m to the -3, m to the -1, the greater of those two numbers occurs in the numerator. M negative 1 is definitely greater than M negative 3 in terms of being more positive, so you should see an M in the numerator. And how much is it greater by? You think the difference in number here, negative 1 to negative 3, that's a difference of 2, hence our exponent here. Similarly with the n, if I compare negative 4 and 3, well, negative 4 is less than 3, meaning the n should be in the denominator. And what is the difference between negative 4 and 3 in terms of integers separation? It's a difference of 7. So you can easily confirm where is the exponent greater? Is it the numerator or the denominator? And that will basically tell you exactly where your final solution is going to end up. It's a really good check on top of the rules that you know, either quotient, product, or power down the road here. All right, so power rule, here we go, we're introducing it. So power rule says if I have a base to an exponent and then raised to another exponent on the outside, what does that mean we do? Power rule, so we had product, which means add our exponents, and that's multiplication of bases. We had division of bases, which subtracted. Power rule is when we multiply. So 2 to the 3 with a 4 on the outside, we're going to multiply 3 times 4 to make our new exponent of 12. Similarly over here, we're going to multiply our exponents m to the 2 with 7 on the outside, or raised to a 7th power. This is going to be m to the 14. We go over here, this 5, what you really need to pay attention to is that it applies to both exponents. So we're going to go m to the 2 times 5, which is 10, over n to the 3 times 5, which is 15, and because they're different variables, they will not reduce. All right, we go over here, and like I said before, power rule applies to everything in the brackets, all exponents. So what we need to do is go one by one. X to the 8 raised to the 2 goes 8 times 2, which is 16. X to the 4 times 2, that's going to be 8, all over x to the 3 times 2 is x to the 6. Now, what we also could have done, and I'll write it over just below actually, what we could have done is said, well, x to the 8 times x to the 4 by product rule, we know this becomes x to the 12 over x3. And then we have 2 on the outside, and then I could have simplified. I've done product rule, now I could do quotient rule. X12 over x3 becomes x to the power of 9, because 12 minus 3 is 9, raised to a 2. And then this would become, by power rule, 9 times 2 is 18. So let's confirm that. That's one way we could have done it, is doing everything on the inside of the brackets and then doing power rule. Or what I've done here is done power rule right away, and now we're going to do product in the numerator here. 16 plus 8 is going to be 24 over x to the 6. And now by quotient rule, we know we subtract the exponents. 24 minus 6 is going to be x to the power of, in this case, 18. So we see that the two solutions connect. Whether I wanted to do product, then quotient, then power rule, or power rule, then product, then quotient, we get the same answer. So that's nice, is that you get a little bit of choice when dealing with what approach you want to take. You just have to know definitively what the rules are doing at each step. All right, next example here. Well, we have 3x in brackets, all raised to the power of 3. An important thing to note here is that the exponent on both of these terms is 1. And by power rule, it must apply to both. It must distribute to both. 3 to the power of 3 times x to the power of 3. And then we can expand this out further. 3 times 3 is 9 times 3 would give us 27x cubed. Okay, now we're going to compare that to, what if 3 is outside the brackets? Well, if 3 is outside the brackets like this, the exponent definitely does not apply to that. Thus, we can say this is going to be equal to 3, and then the power on x, when distributed here, is 1, so it's going to become x to the 3. So we have two different solutions here, because 3 is either included in the brackets, which means it has the exponent applied to it, or it's on the outside as a coefficient, and then only the x would get the exponent. All right, now, probably the most difficult example that we're going to face here, let's deal with this here. So using every bit of terminology we've used so far, if I want to use power rule on this, well, what I want to do is I want to label 1 on top of everything that doesn't have a specific exponent. Okay, now what I can do is say, okay, if I have an odd exponent with a negative on the inside, Well, an odd amount of negatives is going to give us a negative. So what we can do is start by writing a negative here. And then we have 3 to the power of 3 because that 3 will distribute to both. 3 to the power of 3, y, 2 times 3 is 6, multiplied by, now we're going to go negative x squared y3 times 2x. Okay, now we have to look at our negatives here. We have one negative here and one negative here. An even amount of negatives, or negative times negative, is going to give us a positive. So we're actually going to get a positive solution here. This is going to be equal to 3 to the power of 3 was 27 from our previous problem. Y6 multiplied by, we have x squared y3 2x. And do you see how I took away the negatives? Because I said we had a negative here, we had a negative here, so those are going to cross out. They're actually gone. Now, by product rule, we're going to multiply these together and add their exponents. 2 times 27, well, 2 times 20 is 40, plus 14, that's going to be equal to 54, because we just do standard multiplication with our 27 times 2. We're now going to add the exponents of our y. Y6 times y3, that's going to become y6 plus 3, which is y9. And then this is multiplied to x squared times an x1. If we have x squared times x1, we add those exponents together, that's x to the third. So we have 54, y9, x3 is the simplified solution. All right, now combining exponent laws together. So just like the last problem where we had to put a few things together, power and product, or product, quotient, and power all in one problem, that's going to become really popular with these, except these are even a little more involved. You just have to really take them step by step. Okay, so what we're going to do here is we could go in a couple different directions, but the direction I think that's going to be best here is we're going to try and simplify things in each of the fractions independently and then create a crossover in the end here. Okay, so if I deal with the first fraction that's in the brackets, before I even deal with that outside exponent, we have C3 over C7 times D5. Well, where are the C's greater? If I look here, I have 3 and 7. They're definitely greater in the denominator by how much? By 4, because the difference between 3 to 7 is 4. So what I could do is put D5 in the numerator all over C to the 4 divided by, and now in my second fraction, I'm going to simplify this and say if I have D11 over D5, if I look at this, well, the D's are actually greater in the numerator because there's 11 versus 5. And how much is it greater by? A factor of 6. So we're going to say D to the power of 6 over C2. Okay. Now, to really clarify what we're doing there is when I'm saying, oh, we're comparing the numerator to the denominator and figuring that out, I'm actually using quotient rule. C3 divided by C7 is like saying C3 minus 7, which is equal to C to the negative 4, which is equal to 1 over C to the 4. So C goes to the denominator. And similarly, if I have D11 over D5, what am I doing? This is D11 minus 5, which becomes D6. So the 6 should go in the numerator. All right, now let's continue our problem here. What I'm going to do is I'm going to do two different operations here. I'm going to apply that exponent using power rule. So it's going to become D to the 5 times 4, which is 20, over C4 times 4, which is C16. And then I'm going to flip this from division to multiplication. Remember from our number sense section, if I change this from division to multiplication, I must use the reciprocal or change the second fraction and flip everything. Don't change any of the signs. Don't do anything like that. All we're going to do is do the reciprocal and just flip that fraction. So from here to here, we flipped our fraction. Okay, now we're going to continue with this. Remember, when we multiply, we can multiply our numerator to numerator, denominator to denominator. So if I wanted to use arrows to represent that, I could go directly across. And so my next line is going to be equal to D20, C2 over C16 times D20, or D6, my bad. This is going to be equal to, now we're going to use quotient rule on both of these. D20 over D6, that's like saying D20 minus 6. And then I have c2 over c16, which is like saying 2 minus 16 in the exponent. This is going to become d to the 20 minus 6 is equal to 14. C, 2 minus 16 is negative 14. If I have a negative exponent, I need to flip that to the denominator to make it positive. So this becomes d14 over c14. And that would be our final answer there. And I'll make sure to close that to not confuse it. All right, now dealing with negative exponents, we actually just dealt with that above, but we're going to actually really formalize it right here. If I have a negative exponent, if it's in the numerator, it goes to the denominator. If I have something in the denominator and it's negative, it goes to the numerator. So in our first example, these are both in the numerator. What I'm going to do here is I'm going to say a to the negative 6 is equal to 1 over a to the positive 6. It now appears in the denominator as a positive. Similarly, I'm going to change 2 to the negative 3 to 2 to the positive 3 and make sure it's in the denominator. And we know that 2 to the 3 is equal to 8. So this actually simplifies to positive 1 over 8. All right, let's look at our next example here. It's 2 over 3 to the negative 4. What we could do is we could apply by power rule to each of the exponents, this negative 4. Or what I could do is say, if that exponent is negative right here, I can flip my fraction and then apply the 4 in. So here's what I mean. I'm going to do the reciprocal, 3 over 2. I flipped the location of the two numbers that are in the brackets here, and now I can write this as a positive 4, and now I can distribute that to each of the exponents. 3 to the 1 times 4 is 3 to the 4th power, over 2 to the 1 to the 4 is 2 to the 4th power. And then, of course, you could expand this out and get some specific number here, but for just this example, I'm going to leave it at that. All right, now another comparison factor, things in bracket versus out of bracket. If both things are in the brackets and they're raised to a negative exponent, what we need to realize is that this is going to be equal to everything in the brackets brought down and raised to the positive exponent, versus if the thing is, or the negative exponent is only attached to one of the terms and both things aren't attached through brackets, it's going to be equal to 3 over x to the positive 3. Only the term that has the exponent directly attached to it is going to flip. The coefficient that doesn't have the brackets around it or doesn't have that negative exponent directly connected to it is going to stay. And then what we could do is just expand this out like we've been doing before. So I could say this is equal to 1 over each of these things by power rule is going to get the 3 distributed to them. 3 to the 1 times 3 is 3 to the 3 times x to the 3rd. And then the other side, that one's already simplified, so I can't really do much with that. This is going to be equal to 1 over 3 times 3 is 9 times 3 again is 27 x3. So you should get positive 1 over 27x to the 3rd power. And then in the other example, all that moves down is to the x to the 3. All right, now with this example here, what we're going to try and do is simplify the inner brackets, because remember, standard order of operations still applies. Even when you're dealing with exponents, we still want to start with brackets, then move to multiplication, division, then deal with anything in the end in terms of addition or subtraction if it comes to that. What I'm going to do here though is say this is going to be equal to 14. The a to the 5 goes to the denominator. Reason being is because when we look at this, we have a to the 5 that's only connected to the a. If the 14 had brackets around it with the a, so for example, if it looked like this, then the 14 would move with it. But we know because only the a has this negative 5 attached to it, it belongs in the denominator. Divided by, I'm going to simplify the inner brackets here. Standard multiplication applies, 7 and 2. They're going to be multiplied together, so it's 7 times 2, which is 14. And then a1, remember, if it's not written, you got to throw it in there. a1 times a to the negative 4, you add those exponents, it becomes a to the negative 3. Therefore, this is going to become 14 over a to the 5, and then divided by 14 over a to the positive 3. Just like the first case, the 14 is not connected to that exponent. Only the a is. So we're going to leave it like that. I'm going to flip this fraction. So this is going to become, well, this is, I guess, I'll explain it this first way, but then I'll actually show you another way. If I want to flip it or do the reciprocal rule, I can change this to multiplication and make it a3 over 14. And now I can just cross compare this and say, well, 14 divided by 14 is equal to 1. And a3 divided by a5, the a's are greater in the denominator, and they're greater by a factor of 2. So my final solution is actually 1 over a squared, like this. Now, what rule did I just apply there? The rule I applied was saying if it's a3 and then divided by a5, that means by quotient rule I subtract, which becomes a to the negative 2, which is 1 over a to the positive 2. Now, I alluded to there being another way. What we could do is if instead you just wanted to divide right away, so instead of doing the flip rule that we did here, going from division to multiplication and flipping that fraction, instead what we could do is say, what if we just divide right across, just like we did with our multiplication? So if I just simply divide across, numerator to denominator and numerator to denominator, well, what I would find is that 14 divided by 14, and I'm going to do this part in red, is equal to 1 over a5 divided by a3. Well, we actually just figured this out. a5 divided by a3 is like saying a5 minus 3 by quotient rule, which is equal to 1 over a to the positive 2. So whether you want to just divide right across the numerator to the numerator and denominator to denominator and just simplify the solution that way, or if you want to multiply and flip that fraction, you'll end up actually getting the same answer. You see that we got it the same answer regardless. One was just a different operation than the other, but you get the same thing in the end. So whatever you're comfortable with there, sometimes it's easier to go to the further step of multiplication, and sometimes it's easier just to divide right across like that. Whatever you prefer works. All right, now here's a really important piece. This was on your unit exam for exponents. It was on multiple of your quizzes. This is something that's very intentional, and we put it in to make sure that you don't get tricked by this. So we cannot distribute using power rule across a positive and negative sign. So it would be totally incorrect for us to say, yeah, this is x1, y1. We take our 2 and we apply it to both of those. That is completely incorrect, because what does it mean to actually square? Well, if I have x plus y and I square it, this is equal to actually x plus y times x plus y. We write it out twice. And similarly, x minus y squared is equal to x minus y times x minus y. And by distributive property, we would get way more terms than what is appearing in this side here. If we just simply do this, we're totally off base, because here's what it actually equals. If I distribute and I take my x and I multiply it to both, that's going to give me x squared, and I should put an equal sign here. This is going to give me x squared plus xy plus y times x times y times y. This is going to be plus xy plus y squared, which is equal to x squared plus 2xy plus y squared. Do we see how that's a lot different than just simply this? We're actually missing a term here. That missing term is 2xy. So if you just simply distribute, you're totally off on this, and you're actually not getting the right form. So please, if you see this, if you see a bracketed term and there's some addition or subtraction, do not distribute that exponent using power rule across. Okay, so in this one, when we're dealing with rounding and we want to round this to the nearest hundredth place, well, the hundredth place appears right where the blue 3 is here, or that 3. So if I look at the number right behind it, which is a 2, in order for that number to be rounded up or for it to become a 4, we would have to see something greater than 5. Now, if I look at 2, 2 is definitely not greater than 5, so it would not be appropriate. If this is a number that is less than 5, so because 2 is less than 5, that 3 is just going to stay exactly where it is, and we're just going to write this as 2.83. 3 will not be rounded up because the number behind it is not greater than 5. It has to be greater than 5 to round. Now, write this next number in scientific notation to 3 decimal places. Well, if the decimal is currently here, then if I want it to 3 decimal places, what I'm going to have to do here is I'm going to have to say, let's move this so that it is in terms of one number being the leading coefficient. So I'm going to move it a certain amount of times like this, and I want to count that. We're going to move it 1, 2, 3, 4, 5, 6, 7, 8 times. The new number would become equal to 1.43, And then if we want it to 3 decimal places, we see that 9 is greater than 5. And so that number is going to round up. 4 becomes then 5. This is going to be multiplied 10 to the certain power. How many times did we count it again? Well, let's just make sure we moved it 1, 2, 3, 4, 5, 6, 7, 8 times. So this is going to become 8 times because the number is actually significantly large. It's something in the millions. So we should have something that is to the power of a positive exponent because we're symbolizing that we have a very large number. In the opposite case, let's actually deal with this example here. So if I move this and I want to create it in scientific notation to the nearest thousandth place or 3 decimal places, I'm going to move this in front of the leading number here. Because a leading number is something that is 1 or greater. So we're going to move it twice in this case. The number is going to become 5.69, and we wanted it to the thousandth place, which is going to be a third spot. So I'm going to write it as 0. And we have to write this as 10 to the power of, we moved the decimal spots 2 times right, or we took a small number and then made it in scientific notation, which means a small number should have a negative exponent like this. Or to memorize this, you could say, if I move that decimal right, it's a negative. If I move that decimal left, it's a positive. Okay, so there's our scientific notation here, and there's our rounding. So just make sure if you're going to round, that number that's behind the numbers place that you're trying to round to has to be greater than 5, or else you're just going to leave the number exactly how it is. Now, one of the last pieces here, or last problems we're going to deal with, is matching equivalent expressions here. So what we're going to do is say, according to what we're given in the boxes here, there should be a matching answer for that. So we might have to do a little bit of work here in order to make them look like the answers. In the first one, I'm going to look at this and say, well, we have a negative exponent here, meaning both things are going to have to flip. This is equal to 1 over negative 3x squared, because the exponent becomes positive. You keep whatever's in the brackets, just move everything to the denominator or numerator. And then it's going to be 1 over 3 squared is going to be 9. A negative squared, or a negative raised to an even power, is going to be even, or is going to be more specifically a positive number. So negative 3 squared is actually positive 9. And then we have x squared. Okay, let's move on to the next one. The 3 stays because it is just a coefficient not attached through brackets. The x squared moves to the denominator. In our next one here, we know that a positive exponent, or an even exponent of 2 is going to make any negative positive. And we're going to go by distribution of power rule, it's going to become 3 squared times x squared, which is equal to 9x squared. We go down here and we see that we have a negative outside of the exponent. So what this is actually going to become is negative 1 over everything in that bracket moves down and the exponent becomes positive. This is equal to negative 1 over 3 squared, which is 9, x squared, which is x squared. And then this final one here is going to be equal to, or the second last one, the negative stays, and everything that we don't have to move anything actually because the exponent's positive. So we're going to have negative, and then both of these have an exponent of 1. When we distribute it, it's 3 squared x squared, which is going to then become negative 9x squared. Finally, we have something with negative 3 as the coefficient. It's not attached to that negative exponent. The negative exponent is going to go to the denominator as a positive exponent, and there we have nothing to simplify from here. So just remember that if you have a negative or some sort of coefficient that's not attached to that exponent, don't apply it, just leave it where it is. Everything else will move. And then another simple thing to remember here is that when we're dealing with exponents, if it's an even exponent, something like 2, 4, 6, 8, it's going to remain positive. If it's a negative raised to an odd number like 3, 5, 7, 11, it's going to become a negative. Now, our job is just to match up the letters and make sure that we put them in the right boxes here. So I'm going to do that in blue. Which solution matches up with A? Well, if we go to our examples here, we're looking for negative 3 over x squared. That's actually our last one here. So A corresponds here. If I'm looking to match up my solution B, or 3 over x squared, to some box, 3 over x squared, that's actually here. So we can write B here. Negative 9x squared, which one does that line up with? that would be here. So we're going to put C in our middle bottom box. And then we want to match up 9x squared with one of them. 9x squared appears in our third box. So I'm going to put D here. We have 1 over 9x squared, but negative, which means it's going to be our bottom left box is E. And then finally, that only leaves us with one option. F is the 1 over 9x squared. So there was a little bit of legwork we had to do to simplify these and get them in their right form with only positive exponents. Remember, final solutions are always going to be in terms of a positive exponent. If we scan our answers here, do you see how all of the x terms have a positive exponent? That's always how your answers are going to be required, because we want to see that you can do that flip action and you're not going to leave stuff as negatives, because a negative still means there's some operation that can be done